All right, so good morning and welcome to our 26th meeting of Classical Mechanics 1 at CMI. Today is the Thursday, the 23rd of December 2021. This is supposed to be our last lecture. So last time we were talking about some relativistic effects having to do with Lorentz transformations, particular time dilation and length contraction, concepts of proper time and proper length. And using those, we were defining what it meant to be space-like separated and then time-like and light-like separated we were going to go to. So let me share my screen and meanwhile, do you have any questions? All right, if not, we will continue. So you have been given the final assignment, number 9, along with 8. These two will constitute the final exam. There is no separate final exam, so to speak.
So just to clarify, we don't need to we won't get an extra paper from 9:30 to 12:30 on, I think, 28th or 29th.
No, that's correct. You will not receive another paper. What I have assigned is to be done. Yes, I have asked that you read 2 of the chapters we have discussed and suggest 2 questions on one on each of them. You're not required to answer the question, but it will be nice if you just give some hint or some indication of how you might go about it. But that is not, no details are required. You mainly need to formulate a clear question about one topic from each of the chapters. Okay. Yeah. So let me go back to where we were before. So we had defined what we meant by events, what we mean when we say that 2 events are space-like separated. If they are space-like separated, then in the frame considered, the spatial separation, so we have 2 events. Let's call the 2 events A and B, and they have coordinates XATA, XBTB in a certain frame. They are a spatial distance L equal to XB minus XA apart, and temporally they are TB minus TA apart. Now, let us assume that both these numbers are positive, L and T. So if we go to another frame, of course, the values of the coordinates are going to change according to the Lorentz transformation. As a consequence, the same pair of events would have coordinates denoted by these primes. Yeah, and you could determine the spatial and temporal separation of those events as viewed from the other frame. They're not going to be the same L and T. There's some L prime and T prime. And we have derived formulae for L prime and T prime simply by using our Lorentz transformation formula. Now, okay, so that is the setup. Now we make an assumption. Let us consider the case where L is more than CT. So in the original frame, the two events are such that their spatial separation is more than the distance that light would cover over the time t, which is the temporal separation. Yeah. So in other words, a particle would have to travel faster than the speed of light to go from A to B. Now, under such circumstances, we showed last time that no matter by how much you boost, that is, you move to a frame which is traveling at speed v relative to the original frame, the spatial separation L prime is always positive. It can never be shrunk to 0, while the temporal separation could be made positive, negative, or even 0. Yeah. So if a pair of events are such that L is more than CT, in no frame is it the case that the spatial separation can be brought down to 0. Under such circumstances, we will say that A and B are space-like separated. And a special feature of space-like separated events we observed is that there is, however, a frame in which they occur at the same time. And this is the frame that moves at a speed v star given by c squared t upon L relative to the original frame. The formula for this v star is obtained simply by requiring that t prime be equal to 0. If you put this equal to 0, you will find some speed required, and that is this one. So space-like separated events can be made to occur at the same, can be made to occur simultaneously by going to an appropriate frame. Yeah, all right, let me similarly, okay, so maybe a diagram will be nice here. So suppose we have an event which I located at 0, 0. So suppose we have one space and one time direction alone. Could generalize this to more. Suppose we have an event here. Let's call that A. Now, and if a particle travels at the speed of light, then it will cover a distance c in unit time. Yeah, so it will travel in a straight line. Now I'll draw that straight line at 45 degrees by taking the speed of light to be 1 in the units considered in this figure. So this would be the trajectory of a light pulse emanating from A. Well, it could go either to the right or to the left. So I draw two lines. So this is a light pulse trajectory. Now a space-like event, space-like separated event, B, is 1. So suppose this is the frame in which A is occurs at t equal to 0, x equal to 0. Yeah. Now another event could be B, could be here, for instance, B, could be here, for instance, B. All of these events are such that a particle would have to cover a greater distance than light would allow it to cover in the time allotted. Yeah, so here the two are at the same time in this frame, and so you would have to have instantaneous propagation if you wanted to go from A to B. So such events are definitely space-like separated, but so is an event here B prime or B, I'll call this B1 and B2. B2 is also space-like separated because the spatial separation between the two events is this much, and that is that L is more than CT, where T is this much, capital T is this much. Okay, so B1 and B2 are space-like separated from A. Yeah. So is B3. B3 is also of the same sort. Yeah, in fact, every event in this wedge and also in this wedge, all these B4 and so on, they're all space-like separated. So from this figure, we can infer that all events in this wedge and in that wedge are our B's. Yeah, if A is here, then all B's are space like separated from A. We are comparing two events. Right? That is the important thing. We are not comparing two observers, comparing two events. And if a pair of events are space-like separated as determined by one observer, the same holds for any other observer.
Sir, could you repeat the diagram, please? I'm not clear on the B1, B2 part.
Correct. So let me draw the diagram once again. We are considering, let me shrink the bottom part. That's not so important right now. So we have A here. A is an event that in the frame considered occurs at t equal to 0 and x equal to 0. Okay, so that is the event we are considering. Okay, great. Now, if from this event light signals are sent out, they can be sent out either rightward or leftward. Their trajectories would be straight lines, which in the space-time diagram would look like this. I am choosing the slope to be 45 degrees because I'm working in units where speed of light is 1 in this figure. Okay, so these are light pulses, trajectories of light pulses. Now I want to know which events in this figure are space-like separated from A. Answer to that question is all the events in this region and that region. So example, this event B1 is space-like separated from A because it is at a distance L, let us say 1 centimeter from A in this frame, and temporally it is separated by 0, yeah, because both are at the same line of simultaneity. So you can see whether this condition is satisfied. Oh yes, it is satisfied. T is 0, L is 1 centimeter. So it is satisfied. So this B is space-like separated from A. So is this B. Yeah, this is also space-like separated from A. Yeah, of course you have to reverse the signs, but you know, I think you can do that. Same way, this B is also space-like separated from A because its temporal, so its spatial distance from A is the same 1 centimeter, right? Because I drew it like that. It's the same 1 centimeter, but its temporal separation, capital T, is less than 1 because it lies below this line. Yeah, the point here would be labeled 1. This T is less than that. So Siddhant, do you understand how I am determining that B2 is space-like separated from A?
The last part, the temporal separation part.
Yeah, let us find a temporal separation between B2 and A, right? That is our aim. We already argued that the spatial separation L is 1 centimeter, simply because I drew it above that point. The temporal separation is this amount. I am claiming that that distance, time distance, is actually less than 1. Why is that? Because to find the time 1, I have to go space 1, go up to a line of 45 degree and then go to the left. Right? I hope you understand that geometric construction. If this is 1 and this line is at 45 degree, then this point is also at 1. In this case, this T is below 1 and therefore T is less than 1. Yeah, 1 is more than T. Is that okay?
Yes.
Okay, great. So you are now in agreement with me that B2 is also space-like separated from A. By the same sort of argument, B3 would also be space-like separated from A. I mean, the picture is very simple. Any point that is reached from the origin along a line that is sort of at an acute angle to the horizontal, any such point will be space-like separated from A. And therefore, putting all of those points together in a shaded region, we get this pair of wedges of space-like separated events from A.
So you're just graphically comparing that L is less than CT, right? There's nothing new you do.
Absolutely. That is all I'm doing.
Okay. I just spaced on that.
Yeah. Now, with this picture in mind, things are very easy. This is called a space-time diagram. We can now easily describe what we mean by time-like separated events. So again, let us just do that first in words, and then I'll show it in the picture. So on the other hand, suppose you have two events, A and B once again, in that same frame. And suppose L is less than CT. Yeah. So an example of such an event would be here. Yeah, because for such an event, L is this amount. Yeah, because this is A, that is B. The spatial separation is this L. That is less than CT because T is how much? T is this much. T is the temporal separation. And I hope the figure makes it clear that this is less than that because it lies above the 45-degree line. So let us consider such a B, which is at a location such that L is less than CT. Well, physically what this means is that a particle could go from A to B, covering a distance L, going slowly, yeah, because it will have to go, if it goes at constant speed, it will have to go at a speed L upon T, which is guaranteed to be less than C. So a particle traveling at some speed less than the speed of light can go from A to B. So in this case, we will say that it is time-like separated, but to give the justification and to show that this is what this means in another frame. In this case, if L is less than CT, let us look what T prime is. Look at what T prime is. Turns out that T prime is always positive, whereas L prime can have either sign, positive, negative, or zero. Yeah. So T prime is always positive. Let us see why that's the case. I just want to write down the formula for T prime. T prime is equal to gamma times T minus LV upon C squared. Yeah. So if T is more than L upon C, yeah, that's what we have assumed, that T is more than L upon C. T is more than L upon C, then T must also be more than L upon C times V upon C, because V upon C is assumed less than 1. Just multiplying by yet another small number here. And therefore, this difference must be positive. Therefore, T prime is positive. I hope that was understandable. What we have shown is that if L is less than CT, that is if a particle can make it from A to B traveling at a speed less than that of light, then the temporal separation between the two events in any frame is always positive. Under such circumstances, we will say that the two events are time-like separated. They're time-like separated, and the reason for the terminology partly is that there is no frame in which they occur at the same time. They cannot be made to be simultaneous by a choice of frame. However, there is a choice of frame in which they occur at the same location. Yeah. And by what method would you determine that frame? Can you enlighten me on that?
Sir, we'll make x is equal to 0.
Not x. What did you mean to say?
Sorry, L prime.
Yeah, very good. You will make L prime equal to 0. You want to make them happen at the same location. Yeah, even though they are somewhat at different times, suitable frames. So you make L prime equal to 0, put that equal to 0, you will get your V star. You'll get V star is equal to L by T. Yeah, so there is a frame which moves basically along with that particle that has gone from A to B. And in that frame, the two events will occur at the same location, but at different times. Okay. All right. Final case. Oh, so in the picture, let me redraw the picture. Got very congested. So events like this B or even the B that's up here. This B is also time-like separated from A, because in the frame considered here, B and A are spatially at the same location. L is simply 0. Of course, T is not 0, it is some amount, but nevertheless, L is less than CT because L was 0. So all these events that I am putting dots here, all these events are time-like separated from from A. Okay, so so this region is all consisting of time-like separated events from A. Yeah, it's very important. This is all considering pairs of events. So in this case, we are holding event A fixed and looking for B's which are time-like separated. So all of these are time-like separated. Stuff here was space-like separated. Now, of course, the boundary between the two regions becomes the last case of interest. So finally, if L is equal to CT, yeah, then we would say that the events are light-like separated. And that is because a light signal can be sent from A to B, because light would have covered exactly that distance at the speed c over the time t allowed. So, and those we started with, that was the original rays that we wrote. Any two events along these rays are light-like separated from event A. So this L and that L and that L, those are all light-like separated events. All right. So we have classified the points, the events in this fashion. Okay. So that is nice. We can go one step further using these. Yes, please.
So for light-like separation,
yeah,
if the frame is traveling at the speed of light, then they both occur at the same time and the same place. Is that
okay? I
mean, if L minus
no,
CT.
see, we are okay. No, we usually think of frames that do not move at the speed of light. But please repeat. You want a frame that is attached to that light signal. Is that what you're saying?
Yes, that's what I was saying.
Light
because
pulse.
I mean, if L minus CT is L is equal to CT, then
correct.
I think that's what it should come out to.
Yes, yes, you are right. Yes, you are right. Yeah. Sure. Yeah. Yes, the proper distance along a light signal is 0. So yeah, in a sense, that is what you're saying.
Okay, so yes.
Yeah. So sorry, who I'm sorry, I have lost the screen. Yeah. So that was. I'm sorry, who was speaking?
Romit.
Sorry, Romit. Yes. Yeah. So sorry, do you want to just repeat your statement?
So I was thinking that for a light-light separation,
yes,
if the frame is traveling at the speed of light, then both events occur at the same place at the same time.
At the same place at the same time.
Sir,
yeah.
What the Lorentz equation, the gamma factor will become
infinite. Correct. Gamma is infinite. V is equal to C, you are saying. Yeah. So, okay. No, in a suitable limiting sense, T prime and L prime will both be 0. That's what you're saying. You're saying that gamma has gone to infinity. Oh, I'm sorry. I hope you can see my screen. And T is equal to, you are saying that T is equal to L is CT. So T is L by C. T is equal to L by C. And V itself is C. So the quantity in parentheses is also 0. and you're saying that the product is of higher order than gamma. Yeah. Okay. Let me. Okay. Let me rethink what you're asking, and say it more clearly if I can.
Yes, I
Basic.
was just asking the physical significance of it. I think that's fine.
Okay. I'll try to formulate it more precisely and clarify that. Yeah, I mean, as far as the formula is concerned, you are getting something like 0 times infinity. Yeah, so one needs to understand in what limiting sense one is taking that limiting process, and what value it can have. Yeah. Okay. So let me try. If I am able to say that more precisely, I will do so. Okay. So. All right. So the thing I wanted to go to, based on these ideas, is the concept of the principle of causality. So based on these considerations, we bring in this concept of causality. It is only formalizing some things that we have already said. Yeah. So it encodes the idea that signals cannot be transmitted at speeds exceeding the speed of light. So the principle states that in an inertial frame, the event B with coordinates t prime, x prime, y prime, z prime lies to the future of event A with coordinates t, x, y, z if t prime is more than t. So going back to Newtonian mechanics, remember we said that an event lies in the future of A if the time of B is more than the time of A. So that condition we will retain, but that's not enough. Yeah, because from the figure, they may not be causally connected in a physical sense, because all these events B here that I marked here have their time more than the time of A, because time of A was 0, all these times are positive. Yeah, so they would all be lying to the future in that restricted sense, but we would not be able to reach B from A using any light signal or by sending a signal that travels less than the speed of light, because such signals will only be able to go along this line or that line or this way. Yeah. So we want to eliminate such points B as being causally connected to A. So we will say that B lies to the future of A if two conditions are satisfied in this frame, if T prime is more than T and if the two events are either time-like or light-like separated. So that is our definition of causal connectedness. B lies to the future of A if B is either time-like or light-like separated from A, and if T prime is more than T. Okay. So as I said, this will ensure that light or a massive particle, later on we will see that massive particles travel at speeds less than the speed of light. So a massive particle or light can travel from A to B and thereby convey a signal. So in that sense, they are causally connected. And we will say that A and B are causally connected. Space-like separated events are not causally connected. So, and the other point which I want to mention is that if A is in the future of B, actually, here I'm saying B is in the future of A, but it doesn't matter. Anyway, let me correct this. If B is in the future of A, B lies to the future of A in one inertial frame, then one can check that the same holds in any other inertial frame. Okay, that is this conditions of T prime more than T and space-like separation and not being space-like separated are valid in any other frame also. Okay, so This picture summarizes the situation. I mean, it is just a repetition of the figures I've been drawing, just extended to 2 spatial dimensions. And I can bring in this concept of a cone also, though I don't want to dwell on this very much. If you have 2 spatial directions, that is x and y, and time running upwards, then and you have an event O over here, which we used to call A, then light signals that are sent out from O could go in any direction, x direction, y direction, or other directions on the xy plane. So their trajectories in a space-time diagram would lie on the surface of a cone with apex at the origin. Yeah, cone with apex at the origin. And that is called the light cone. So the light cone is the locus of trajectories. I mean, the surface formed by the trajectories or the world lines of light rays emanating from the event O. So that is a light cone. Previously, it was just a pair of straight lines in one spatial dimension. Now it becomes a cone. And the time-like events are the ones that lie inside this cone. So these are all time-like events because a particle would have to cover a shorter distance and it's allowed more time. So it can go slow, can still reach there. Yeah, so these are all time-like events. The time-like events are the ones inside the light cone. And space-like events relative to O, I'm saying, space-like separated events lie outside the light cone. Okay, so the things outside the light cone, all here and here are all space-like separated. Yeah. Okay. Any question about this concept of time-like, space-like separation?
Could you just zoom out a little bit?
Please repeat yourself, Siddhant.
Could you just zoom out a little?
Zoom out. Yes. Okay. Yeah.
Sir, I had a question.
Yes, Gautam. Yeah.
Sir, so we're assuming that V is less than C. I just wanted to ask, where was the first time that we assumed this?
The first time, I think, was when we were deriving the Lorentz transformation formula. When we drew that, used the Pythagoras theorem to determine y prime equal to y. Yeah, we certainly made that assumption here. Okay. Yeah, if not before. So yes, when we derived the formula for the Lorentz transformation between frames, it was done for a frame moving at the speed less than that of light. We have not considered any other possibility. Yeah.
Okay.
So as far as I remember, this is the first place.
Okay, thank you, sir. And as another question related to this, so the idea behind the principle of causality is that if two events are space-like separated, then a signal cannot be sent.
Exactly.
And so we say that, and so we have sort of got the principle of causality from this, right, sir?
Yeah, but I mean, it's motivated by that. Yeah.
This seems slightly circular to me, because it seems that we're assuming speed of the speed of like we can't exceed the speed of light, and then coming at the result that we can't exceed the speed of light. No, so I think I'm misunderstanding something.
No, okay. You are right in your feeling in a sense. Let me say, see, this is an additional postulate. It is not coming from the principle of relativity or the constancy of the speed of light. This is an additional postulate motivated by experimental considerations, which is theoretically consistent as well.
Okay, that makes sense.
So this is really a new postulate in the theory of relativity.
Okay. Yeah. Okay, got it. Thank you.
Based on our observation that we are not seeing things traveling faster than the speed of light, and so we want to encode that in our theory. Okay.
Sir, I also had a question. If you have three events, let's say A, B, and C, and A and B are like, causal, like a signal you like between them traveling at less than the speed of light,
Yes.
can be sent. And
Yes.
same thing between B and C. Is if you take the light, but if you take the light cone about a different origin for B and C, does that mean A and C will not be causally connected? Like, is that even possible, or does if A and and B are causally connected, B and C are causally connected, then A and C also have to be causally connected?
You are right. If A can send signals to B and then B can send signals to C, these are all events. That's very important. These are events. So then the question is, can A communicate with C? Answer is yes, through B, as you have just set up. So C is causally connected to A. Yeah. But you are right. The cones that we draw were originally for A. Yeah. So this is, so B is somewhere here. B is this event. Now A is causally connected to B because a particle moving less than the speed of light can be made to reach B from A. Now you consider the second event, which is somewhere here, maybe, sorry, third event, which B can communicate with. Now, of course, the light cone around B is to be newly drawn. I can draw it afresh here. And so B can send some signal to C. The fact remains that A can send a signal to C. Yeah.
So, but what if C lies outside A's light cone, but still within B's light cone? Like, I mean, the way you've drawn it right now doesn't, you have to extend it really far for that. But there will be a region where B's light cone is not actually inside A's light cone as well, right?
Well, the claim is that this assertion you have made now is not true. You try to draw pictures, you will not succeed in that. All the light cones you can draw for all the B's.
So I guess the
yes,
lines of the cone or the triangle that we've drawn will have the same slope. So
they're all 45 degrees. The light-like signals are all at 45 degrees. So even you're thinking of some B that is very, very close to this edge or something like that, right? So, but I can still extend them out there.
Yes, sir. I think it should always be contained in A's cone.
Yeah. So this, suppose my new B is somewhere here, its light cone will still lie within original A light cone. Anand,
I think I understand now. Sorry, sir. I was thinking of actually changing the frame and then because then you would rotate the
okay.
Sorry,
yeah.
I was thinking along those lines, but okay, this makes sense.
Sure. Yeah. Yes. So this is a transitive relation in that sense, that if B is causally related to A and C is causally related to B, then C is causally related to A. In that sense, it is true. Yeah. I presume you have heard of the concept of a relation in mathematics, in theory of sets. A transitive relation. Okay, so much for this story. I want to then spend a few minutes giving one application, and partly also because of some questions we received last time on time dilation. What does it really mean about these clocks carried by different observers? So I want to give a very practical example where time dilation is very important. Not only time dilation, but also like contraction. Both are very important. So we will briefly consider the study of a particle called a muon. So the muon, there are two of them. There's the mu plus and mu minus. They're antiparticles. So let's consider mu minus. It is a lot like the electron. It's just a much heavier version of the electron. Other properties are very similar to the electron. However, the muon is unstable. It's an unstable particle. So mu minus decays to electron plus antineutrino, electron antineutrino, and muon neutrino. But the main point is that it is unstable, it decays. Yeah. Now these muons are produced in the upper atmosphere through bombardment of the nitrogen, oxygen, and all these molecules by cosmic rays. By cosmic rays, we mean protons, which are coming from outer space. So when these protons come and bombard, you have these collisions, and these muons are produced in those as byproducts of these collisions. Now, as I just said, a muon decays to an electron and a pair of neutrinos. Okay, the details of the decay are not important for us, but the main thing is that just like any other radioactive decay process, the decay of muons is a random process. So we cannot tell if you have a muon in your lab in some container, you cannot tell when it is going to decay. But you have 1 million muons, then you can tell on average how many will survive after some time. Okay, so that is predictable. So on average, when they are at rest in the lab, muons have a lifetime of 2.2 microseconds. What that means, okay, I'm not devoting too much to this radioactive law, but what that means is that if we start with a large number of muons, n of 0 at time 0, then after a time t, the number of muons that survive is found to be given by this radioactive decay law, which says that n, the number of muons that survive at time t, is approximately equal to the number that was initially present times this exponential damping factor e to the minus t upon tau, okay, n of t by n of 0. So this is the fractional number of muons that survive, or any decaying particles, t upon tau. So tau is called the lifetime or mean lifetime. Yeah, and that is about 2.2 microseconds for the muons. Okay. So this is what is seen in the lab. Now, we want to study what happens to these muons as they come down the atmosphere. So if muons travel at the speed v, yeah, then on average, they would cover a distance given by, average distance given by v times tau. Okay, because after time tau, on average, a muon would decay. Some muons will survive more, some will not have decayed, yeah, but or some may have decayed earlier. But on average, a muon will cover a distance L given by v tau if it is traveling at the speed v. Now, for a moment, we will suppose that the lifetime of moving muons is also tau. Okay. Now, that assumption turns out to be wrong, but I just want to make that assumption, see what goes wrong, and then come and correct it. Yeah, so yeah, so now, so as I was saying, muons that travel at a speed v will roughly cover a distance v tau before decaying on average. Now, high energy muons in the atmosphere, yeah, travel at close to the speed of light. Okay, so to a first approximation, we can even take that v to be roughly c, okay, just to get an estimate of how much distance they can cover. So, well, if you put on 2.2 microseconds and speed of light there, yeah, you can compute that the mean distance that muons cover before decaying is 660 meters. All right. Okay. Now, suppose the muons are monitored at 2 heights in the atmosphere. Okay, so maybe one location may be a reference location, which could be in the atmosphere, or yeah, maybe at the top of a hill or mountain, and another location which is below. Okay, maybe on the ground or in a mine, yeah, some gold mine or coal mine below the ground. So in the experiments that were performed in the late 1930s in the United States, this distance between the upper observation point and the lower observation point was L is about 2000 meters. Yeah, this is quite a bit. Yeah, I mean, for instance, Chennai is at 0 mean sea level roughly, and Bangalore is around 980 meters. Yeah, so this is twice the height of Bangalore. Yeah, like in Nilgiris or somewhere. Okay, so now suppose you monitor the number of muons at the original height and also after they descend by height L. Okay, so we'll call those n of 0 and n of L. Yeah. Now, muons take how long to cover this distance? Well, their distance is L and they roughly travel at speed c. So they will take a time t of L by c seconds to cover this distance. So based on that, we would expect the fraction of muons that survive this journey. Okay, this is the hill and this is the, what did I call it? Mine. Yeah, so some mine, that's the hilltop. So the number of muons at the bottom of the mine relative to the number that were there at the top on average should be given by n of t by n of 0, okay, where t is the time taken to cover that distance. So we can write that as e to the minus t by tau, and for t I will substitute L by c. Okay, so this is e to the minus L by c tau. So putting the numbers in for the specific experiment that was conducted, this was done by Bruno Rossi and others, late 1930s, 1940 or so. If you put the numbers, that is L is 2000 meters and C tau, this example it comes to around 660, then you find that the fraction that survived is about 0.048. So about, you would expect about 5% of the muons to survive. Okay, this was the expectation. However, measurements at the top of the mountain and at a mine 2000 meters below showed that a much larger fraction of the muons survived. Okay, so they were surprised to get a much larger flux of muons at the bottom. Now, this puzzle was explained by time dilation. Now, what is the, as well as length contraction, you can take both viewpoints. So let me just mention that briefly. So in the Earth reference frame, Earth's frame fixed on the Earth, the clock traveling with the muon appears to run slow. So the muon's body clock appears to run slow according to the earthbound observer. So for an observer on the Earth, the mean lifetime of the muon is not tau, 2.2 microseconds, but actually gamma tau. That's what we discussed yesterday, 2 days back, that according to the earthbound observer, the muon is traveling at a constant speed. So the clock attached to the muon would run slow. A time tau according to the muon's clock appears dilated according to the earthbound observer, who would assign a time gamma tau to the lifetime of the muon. Now, for the case studied, if you take the velocity of the actual muons, it is not the speed of light, it is slightly less, but nevertheless, it turns out that gamma is roughly 3 in that case. Now, taking this into account, the expected number of muons that would survive this journey as a fraction of the original number of muons, n of L by n of 0, is given by e to the minus L upon c gamma tau. Yeah, so instead of tau, I must put gamma tau. That's the main difference. So if you put the numbers in, basically previously you had 2000 upon 660, now becomes 3 times 660. So, and then you're taking e to the power of minus that. So if you put the numbers in, it turns out you get a slightly larger number. I mean, this is, okay, 36%, whereas you were expecting much less. Yeah. So that is one very vivid demonstration of the reality of time dilation and what effect it can have. So moving muons tend to live longer than stationary muons in the lab. Okay, so this is this now has experimental support. You may ask the question, how does the same situation look to the muon? Okay, because we said there is some sort of reciprocity Yeah, we have to understand it from the viewpoint of the muon as well. So suppose you go to the rest frame of the muon, then the Earth is approaching the muon, and the distance that the muon has to cover, previously we said it is 2000 meters, but according to the muon, because it is moving, that height between the hilltop and the mine shaft, which in the Earth frame is 2000 meters, according to a moving observer, I mean a downward moving observer, that distance is not L equal to 2000, but L prime equal to L divided by gamma. And therefore, according to the muon, it needs to cover a shorter distance, because gamma is more than 1, needs to cover a shorter distance. It still lives only 2.2 seconds. According to it, it has only a lifetime of 2.2 seconds on average, but it has to cover a shorter distance, and therefore more muons will cover this distance before decaying. And this is the explanation for why there is a larger number of muons observed in the mine shaft than you might otherwise expect. Okay, so what is the invariant quantity here? The invariant quantity is here what you measure, that is the flux of muons in the mine shaft relative to the flux of muons at the top of the hill. So this is an experimentally determinable number that you have to predict whatever method you wish to use, whether you want to work in Earth's frame or in the muon's rest frame. And either way, you will find that this flux is larger than if you ignore these relativistic effects. Okay, so the message is that one needs to ask a physically meaningful determinable quantity, and then you can determine it by different ways, different frames. Okay. Yeah, so I hope this will at least help slightly based on the questions from Ripunjay and others last time. As to what the actual effect of this time dilation is. Okay, any question about this? Okay, if not, let me go to what is probably we have time for only one more short topic. And that I want to discuss is the relativistic rule for addition of velocities. So let us understand what this is. So, okay, so as before, let S and S prime be two frames with S prime moving along the x-axis at velocity Vx hat. So suppose S prime is moving to the right relative to S, and let us suppose the two frames coincided at t equal to 0 for convenience. Now, suppose a particle has a velocity with components u prime x, u prime y, u prime z, as determined by the observer in frame S prime. Okay, so a particle is moving, yeah. So it has a velocity u prime relative to S. Okay. Particle has velocity u prime relative to S. One wants to know what is its velocity as measured by an observer in S, if its velocity is u prime in S prime. Now, we can first answer this question in Galilean relativity, in non-relativistic mechanics, based on Galilean transformations. The answer is very simple. It is what you believe is that the velocity as viewed from S is equal to the velocity as viewed from S prime plus the relative velocity between the frames, which was V. Okay, so S prime moves at V relative to S. So this is the relative velocity, and so you just add them, you will get the velocity as seen by S. Now that works for most of our purposes, like a person walking inside a train and somebody wanting to know the velocity of the person relative to the railway station. Yeah, for such purposes, this works. However, there is a problem if you want to apply it to particles that are moving closer to the speed of light, or frames that are moving closer to the speed of light relative to another inertial frame. And you can see that problem if you put in some numbers here. So suppose V, the velocity between the frames, suppose it is c upon 2. Yeah. So S prime moves at c by 2 relative to S. And let us suppose that the particle that is being observed from S prime moves at 3c upon 4. Okay. Then, according to Galilean transformations velocity addition rule, the particle would appear to have a speed which is the sum of the two. Yeah, 2c upon 4 plus 3c upon 4, which would be 5c upon 4. So it would appear to have a speed 5c upon 4 according to the observer in S. In other words, an observer in S would say that this is a superluminal particle. Yeah, so this would suggest that particles can move faster than the speed of light by going to an appropriate frame. And thus transmit signals between space-like separated events in this frame. Okay, now this is a little bit problematic based on what we said about causality. And also, besides, we don't actually observe this thing happening. So we want to understand how to understand this velocity additional rule when we use Lorentz transformations in place of Galilean transformations. Okay, so what do we find when we do that? Okay, so so the aim is that we seek a velocity addition formula in special relativity that will help us answer this question. This was originally derived by Einstein, so it's called Einstein velocity addition formula. So let us see how it is derived. It's fairly simple, but you just need to keep the ideas clear. You need to first define quantities. So let us define the velocity components of a particle in the two frames. So what do we mean by the x component of the velocity in frame S? Well, we mean the quotient of the displacement divided by the time taken in the limit where the time taken goes to 0. Okay, that's what we mean by the x component of velocity in frame S. In a similar manner, you can define the y and z components in velocity in the frame S. In an analogous manner, the velocity components in frame S prime are given by the ratio of the displacements in S prime, so delta y prime by delta t prime, limit delta t prime goes to 0. Okay. And similarly for z and x components. Okay. So this is what we mean by velocity components in the two frames. Our aim here is to relate these velocity components. Okay. We want to relate ux to ux prime. They should be related somehow through the appearance of the v, which is the relative velocities of the two frames, between the two frames. Yeah. So to do this, relate the displacement and time intervals in S and S prime, we will use the Lorentz transformation formulae. All right. So since we're talking about displacements, we need two events. Yeah, we need two events. So let us suppose in the primed frame, you have two events. I mean, they are nearby events because we're taking limit to 0. So there is an x1 prime, t1 prime, an event, and then an x2 prime, t2 prime event. These are the coordinates of two events in the primed frame. And we can ask what are their coordinates in the unprimed frame? Well, simply apply the inverse Lorentz transformation that we derived last time. So inverse Lorentz transformation means all the v's will come with plus signs. Yeah, so that is all it means. Use the same formula that we derived last two classes ago. The x2 coordinate of the event x2 prime t2 prime with coordinates x2 prime 2 prime is given by gamma times x2 prime plus vt2 prime. Same way x1 is gamma times x1 prime plus vt1 prime. T2 is given by gamma times T2 prime plus X2 prime V by C squared. Okay, so I invite you to write this formula yourself by starting with the Lorentz transformation. Okay, but the upshot is that we can find the coordinates of those two events in the unprimed frame. Having found the coordinates, we can define the separations. The spatial distance between the two is delta x, x2 minus x1. Delta x prime is x2 prime minus x1 prime. Delta t is t2 minus t1, and delta t prime is t2 prime minus t1 prime. Okay, so I hope you are with me. Any question?
Sir, just could you confirm the direction of velocity v you've taken?
Yeah, see, the direction of velocity actually doesn't matter too much. Oh, v. Okay, yeah. So v is the velocity between the two frames. That has been taken along the x direction of s. So this was s, and s prime is moving with velocity v relative to s. Yeah. So this is x, that is x prime. Okay, great. The particle itself need not be moving along the x direction. Particle may be moving in some direction whose velocity I write as u prime.
Yes, sir.
Okay. All right, good. Now let me then proceed to calculate the velocity components in the two frames and then relate them. This is not difficult at all. First, we compute the displacements delta x by taking the difference x2 minus x1. So if I take the difference between these two formulae, I will get gamma times x2 prime minus x1 prime, which I will write as delta x prime, plus v times t2 prime minus t1 prime, which I write as delta t prime. Okay. So what is this? This is a relation between the displacement in the unprimed frame and the displacement and temporal separation in the primed frame. The delta y is unchanged. So delta y is equal to delta y prime and delta z is equal to delta z prime, because the two frames are in uniform motion only in the x direction relative to each other. But importantly, delta t is non-trivial. So if I take the difference between t2 minus and t1, I will get gamma times delta t prime plus v upon c squared delta x prime. Okay, so one just needs to be a little patient and write down this formula carefully, and then the answer is very easy to get. So let us see. This is a nice calculation. So let us compute ux. Okay, so ux is the x component of velocity of particle as viewed from frame S. Okay, that is what ux is. Well, by definition, it is a limit of the difference quotient delta x by delta t. So I substitute for delta x and delta t from equation 126. Numerator is gamma times delta x prime plus v delta t prime. Denominator is gamma times delta t prime plus v upon c squared delta x prime. All right. So now we are ready to do some cancellation. The gammas cancel. And then we will divide numerator and denominator by what? Please tell me.
Delta t prime.
Very good. Yeah. Because our objective is to relate the velocity components in S to those in S prime. So on the right hand side, we are going to get velocity components in S prime. So if I divide by delta t prime, the first term is going to become ux prime. The next term just becomes v. Denominator becomes 1 plus v upon c squared times ux prime. Okay. Yeah, so this has the first of Einstein's velocity addition formulae. Ux is not just ux prime plus v. That is true only in some non-relativistic approximation. There is a correction factor which in the denominator looks like 1 plus v ux prime upon c squared. Okay. Now, please tell me what you expect of uy and uy prime. Yeah, y prime and y are the same. But what about the y components of velocities of the particle as observed from the two frames? Would they be the same or not?
No, sir, because the denominator will have those correction terms.
Correct. And okay, that is true. But for what reason are those correction terms coming in?
Because of delta t, t prime.
Correct. Yeah, the times of the two events, the time intervals, delta t and delta t prime are not the same. Yeah, so delta t is related to delta t prime in this formula. So even if delta y is equal to delta y prime, which is true, nevertheless, the delta t is not the same as delta t prime. So let us write the formula. Uy, it is the y component of the velocity of the particle as observed from frame S. It's given by this difference quotient limit delta y by delta t. For delta y, we simply substitute delta y prime, that is unchanged. For delta t, we substitute gamma times delta t prime plus v delta x prime upon c squared. Now we take the limit, we divide by delta t prime, numerator and denominator. And so the numerator will become uy prime. Uy is equal to uy prime, which would have been the Galilean result. But now you're dividing by gamma times 1 plus v upon c squared times ux prime. So that is the new formula due to Einstein. There is a very similar formula in the z direction that is identical. The x, z and y are identical. You replace y's by z's. So uz would be given by uz prime divided by gamma times 1 plus v ux prime upon c squared. Okay, so these three formulae give you the velocity addition rules in special relativity for motion along the x direction, relative motion between two frames. We can do the converse also. We can write the velocity components as viewed from S prime in terms of the velocity components is S, invert this formula, and that is obtained simply by reversing the sign of V. So I can write it down easily. I have written all three formulae here. I will read the first one at least. Ux prime is equal to ux minus v divided by 1 minus vux upon c squared. So this is what it is. The other two formulae, the orthogonal direction components of velocity, the numerator doesn't change. U prime y is the same as uy, but divided by the same factor in the denominator as we got before, except that there's a gamma also. For x, the gamma cancelled, numerator and denominator. All right, so this derivation is straightforward, just that one has to write the formula and keep the definitions in one's mind carefully. Okay, so if you go through it carefully, you will get this result. There is nothing deep or difficult about it. So these are Einstein's relativistic velocity addition formulae. Now, in the non-relativistic limit, namely where V is much less than C, well, when V is much less than C, gamma goes to 1, right? Remember the gamma was 1 upon square root of 1 minus V squared upon C squared. So when V is much less than C, gamma goes to 1. And not only that, this V upon C squared factor will become very small. V upon C factor will become very small, and we can ignore these correction terms in the denominator and recover the non-relativistic formula which said that ux is equal to ux prime plus v, uy equal to uy prime, and uz equal to uz prime. Okay, so the Galilean relativity, non-relativistic mechanics, orthogonal velocity components are unaffected. But in special relativity, they are affected because the times are not common to both frames. So though the boost is only along the x direction, uy is not equal to uy prime because t and t prime are not the same. Okay, so that is worth bearing in mind. This has lots of interesting consequences when you study collisions and so on. Now we can go back to the numerical example we started with. There we had a particle which is moving at 3/4 the speed of light in the horizontal direction, and observed from a frame which is itself moving at c upon 2 relative to some s frame. Yeah, so s prime moves at c upon 2 relative to s, and the particle moves at 3c upon 4 relative to s prime. So if you simply add these two, you get 5c upon 4, which is too much. But if you use this new Einstein velocity addition formula, ux would be given by the sum of these two, 3/4 plus 1/2 divided by 1 plus the product. Okay, so if you put the numbers in, numerator remains 5/4. Well, there's an overall c. The c is giving you the units, and denominator becomes 1 plus 3/8. So that is 5/4 divided by 11/8. If you cancel the 4s, you get 10c upon 11. Okay, so as viewed from S, the particle which was traveling at 3c upon 4 relative to S prime is reckoned to travel at 10c upon 11. Yeah, 10/11 the speed of light rather than 5/4 the speed of light. Okay, as Galilean velocity addition rule would have suggested, as the Galilean velocity addition rule would have suggested. Okay, so and one can take the general formula and also show that no matter what ux prime was, ux can never exceed the speed of light. Okay, so simply by going to another frame, the particle's velocity cannot exceed the speed of light. Now, in the limiting case, this is also interesting. The limiting case where the particle is actually a light pulse moving at the speed of light in frame S prime. So ux prime would be c then. So if you put that in, let's go back to our formula. Ux is equal to ux prime plus v divided by 1 plus v ux prime upon c squared. Okay, this was our velocity addition rule. If you put this in, that is, you assume the particle was moving at the speed of light c. Yeah. Then ux, well, let me compute it. Hope I get this right. C plus v numerator divided by 1 plus v c upon c squared. So c plus v upon 1 plus v upon c. So simplifying further, I will have c plus v divided by c plus v divided by c. So this is c. So if ux prime is equal to, oops, not 0. Ux prime is c, then ux is also c independent of v. Okay, that is the important conclusion, that no matter by what velocity you boost your frame, the speed of a light pulse for both observers is one and the same, c. Okay, so this was a feature that we wanted. That is how we derived the Lorentz transformation. We encoded it. So no wonder it is also consistent with the velocity addition rule. Okay. So this confirms that the speed of light is the same for both observers. Now, this question was already asked. Can we accelerate a massive particle to the speed of light? Well, it can be shown that this would require us to transfer an infinite amount of momentum to the particle. I have not yet discussed the momentum of particles. Turns out there's a formula for the momentum of a particle which is moving at a velocity v. It's given by gamma mv. Okay, so mv is the usual non-relativistic velocity formula. In relativistic special relativity, it is corrected by this gamma factor. Yeah. And if you want its speed to approach the speed of light, your gamma is 1 upon square root of 1 minus v squared by c squared. If you want that to reach the speed of light, v, then the gamma would go to infinity and the momentum would have to be made infinite. Yeah. And to impart an infinite amount of momentum to a particle, you would have to supply it with an infinite amount of energy as well in a particle accelerator, for instance. So it costs an infinite amount of energy. So in practice, it's not possible. However, it is possible in principle to accelerate a particle to any desired speed less than c. Okay, so that is routinely done in particle accelerators, but you can't reach c if particle is massive. So along with this relativistic momentum formula, by the way, I should comment that this factor gamma m is sometimes called the relativistic velocity, relativistic mass. So m is called the rest mass or Newtonian mass. I mean, it's just the mass in Newtonian mechanics. Yeah, but more accurately, it is called the rest mass of the particle. It's the mass that the particle has when it is at rest. So the product gamma m is called the relativistic mass. That can depend on the speed of the particle. The rest mass doesn't depend on the speed of the particle because it's defined when the particle is at rest. Okay. So here we are. Along with a relativistic formula for momentum, there turns out to be a relativistic corrected formula for energy of a free particle. That is given by rest mass times c squared again times gamma. Okay, so that is capital M times c squared. Yeah, but it's important to bear in mind that the small m is the one that is quoted. The rest mass of a particle is what is an intrinsic property of the particle, whereas the relativistic mass depends on its velocity. So it will depend on its motion. So in the problem set 9, there are a couple of questions about P and E, which I invite you to try out. Unfortunately, I don't have time to explain where these formulae came from. The message is that to discover this formula for P, one requires that whatever it is, it must be a conserved property of particles in collisions. You want the momenta of particles to be, total momentum to be conserved. If you impose that restriction in collisions, it's possible to derive this formula, but that is for some other time and place. So as far as this course is concerned, this is as much as we have time for. Do you have any questions about either this velocity addition or things we have just said?
So you told how the momentum would change and the relativistic mass. Now, what would be the gravitational field by this mass traveling at some speed? Will it change? Okay, gravitational field.
Gravitational field is a different question. No, I mean, see, a particle can have a mass, and it is really only the. Okay, I mean, your question is, yeah, any massive particle or even massless particles like photons do feel the force of gravity. Yeah. So the gravitational mass is still the same as the inertial mass of the particle. Yeah. Okay. I think maybe to discuss this issue in more detail, one really needs to study a different topic. Mm, yeah. So let me not try to give some short answer over here because we have not even set things up. But the rest mass continues to be the gravitational mass. Yeah, I mean the inertial mass is still the gravitational mass. Yes, but yes, when one looks at the coupling to gravity, one has to be more careful. The force felt doesn't depend just on the rest mass. So, for instance, a photon can be attracted to a star or to a black hole, and that photon has a zero rest mass. Nevertheless, it feels the force of the star, and that force then depends on the energy that the photon possesses. So one has to study this in more detail to understand. So yeah, simply because the rest mass is zero, we cannot conclude that the gravitational force is zero. So that is wrong. That is not correct. So this requires a more detailed study. Yeah, so which we are not performing over here. Which I am. Yeah. But one should bear in mind that even massless particles can feel a gravitational force. So the force is not entirely encoded simply in the rest mass of the particle. Okay. Any other questions?
Yes, sir.
Yes. Yes, Shubham.
Yes, sir. When you say that massless particles can feel gravity, are you saying this from the perspective? Are you saying this within the framework of Newton's gravitational laws or something else?
No, they're not within Newton's gravitational laws. Yeah, this discussion is actually doesn't belong here. Within the context of Newton's gravitational laws and Newtonian mechanics, there is no such thing as a massless particle. A massless particle would have zero momentum, according to Newtonian mechanics. So such a particle would also yeah. So if m was zero, then massless particles cannot carry momentum, and you can. I mean, it's not a very meaningful concept, massless particles. Whereas in the relativistic theory, it is possible to discuss a particle whose mass is zero, but which is traveling so fast, namely at the speed of light, that gamma has gone to infinity, such that the product gamma m is finite and non-zero, so that the particle can have non-zero momentum. So it is in that context that one is talking about it. And furthermore, one has to expand from Newtonian gravity into Einstein gravity to talk about the force that such relativistic particles or massless particles would feel from a star. And it is in that context that we are saying it, not in Newtonian gravity, no.
Okay, sir.
Yeah, thank you for checking that. Yeah, so massless particle is a concept that doesn't make sense. At least it cannot be given a non-zero momentum in Newtonian mechanics. It is only in special relativistic mechanics that one can have a massless particle having non-zero momentum as well as energy. And then one can think how those properties of the particle can be affected by other particles or by gravitational fields. Any other question?
Sir, sorry, go ahead.
Okay. Ishan is asking. Please go ahead. Yeah.
So I had a question regarding the Ensign paper.
Yes,
So
please.
In the last question, what should be the level of the questions that we shall give? I mean,
Okay.
shall it be?
All right. See, I want you to. Okay. It is partly up to you. I'm not expecting some very deep question, but I also would hope that you don't ask some trivial question like what is 2 + 2 or yeah, what is x upon 4x and such things. Yeah, so please try to ask some question that is relevant to the topic discussed. Or you're asking what is the level. Okay, just as a point of comparison, we have asked questions in these 9 problem sets. Now, you don't have to ask the most difficult question among them, but something of that sort. But don't worry so much. Ask some question that has of some interest to you based on the topics studied. That's all. Yeah, it's okay if it doesn't have to be some very complicated thing for which you don't know the meaning of the question or the answer. No, we are only asking about something you have studied.
Okay, sir.
Yeah, I hope that helps. Yeah, so that was Ishan, right? I forget your name, Ishan Banerjee?
Yes, yes, sir.
Okay, thank you. Yeah, so Siddhant was asking something.
Sir, I had the same question.
Oh, yeah, same question. All right. So again, just to clarify, any question about the topics studied, and just try to make sure the question is asked clearly. Yeah, that is a very important part of our enterprise, our studies. We have to be able to clearly ask our questions, then we can start looking for answers. And yeah, I'm not asking you to write the answer. If you want to give some hint or some idea as to the orientation, you are welcome to mention, but I do not expect you to write the answer to the question you pose. Just ask a clear question about the topic. That will do. Yeah. Any other questions?
Yes, sir. I had a question about what exactly we mean by non-relativistic limit. Sir, so in such a condition, do we assume that C is finite and V is just much smaller than C, or do
Correct.
we assume C goes to infinity?
There are different ways to view it. I mean, strictly speaking, C is never infinite. C is a finite number, and we are considering the limit where speeds of particles in inertial frames are much less than the speed of light, and the speed of other inertial frames are much less than C also. Okay, so you may be talking about two different frames, then the other frame would be non-relativistically moving relative to this one if its speed is much less than the speed of light relative to the original frame. Yeah, so yeah, C is never infinite. We are really taking V upon C and then letting that go to 0. Now, in practice, in many formulae, you can get this limit simply by sending C to infinity, right? So in specific context, it is possible to do that. Like over here, if I want to know what happens to gamma in the non-relativistic limit, a naive way to simply put C going to infinity, this term goes away and you say gamma equal to 1. But that will only give the leading approximation. If you want the next order correction, you need to expand and do something. So strictly speaking, it is really V upon C going to 0.
Okay,
C is an absolute constant that is not being changed.
Okay.
But sir, C going to infinity gives the correspondence between relativity and Newtonian mechanics. So is it more of something you do just at the theory level rather than for any particular situations?
Let me say that again. The sentence C goes to infinity is physically meaningless. You can only say the sentence C is large compared to the velocities of particles and observers considered. That is a meaningful sentence, which encodes what you want to do. We cannot talk about a dimension-full quantity being infinity or something. We have to always talk about dimension-full quantities being large compared to other dimensional full quantities of the same dimensions. So when we say C is infinity, what we really mean is that C is large compared to the velocities of other particles being considered. Sorry, this was Anand. I'm sorry.
So first it was Gautam, then it was
yeah, okay, I'm permanently confused between you two. I should not be the case. But did that clarify either of you?
It clarified my question, sir. Yeah.
Okay, very good. Okay, so Anand, were you asking?
Mine too, sir. Yeah.
Oh, you're both asking unrelated things.
It's like yeah, mine was after what Gautam said. I had another one related to that, which I asked, and you answered that. Yeah.
Oh, okay, fine. Okay, excellent. Yeah. So any other questions?
Sir, in the case of light, you said that M will go to 0 and gamma will go to infinity, but gamma M will be finite, right?
Can be finite, yes.
Okay.
Yeah, can be finite, yes. The product, it depends on the state of the light. Yeah, it depends on, the gamma is definitely infinity, M is definitely 0, but the product can have a non-zero limit. And depending on that limit, you will get different types of light. Those different lights will have different colors, different frequencies, and different momenta. So the nature in which that limit is taken to has to be considered carefully. And there are many different light limits, and they lead to different types of light. Even our eyes can tell the difference.
Okay, sir.
Yeah. Any other question? Okay, that was Milan Paul. Anybody else? Any questions?
Sir, not a question, but could you upload the whole notes on the page after?
Yeah. By whole notes, what do you mean? Up till here is what the course ends here.
No, I mean, like I think there's something that we hadn't covered, right? So
correct. I mean, that was concerning this relativistic momentum and energy. Oh, yeah. Is that what you are asking about?
Yeah.
Okay, sure. I will try to. I'll try to include that also. Fine. Okay, sure. So that was Swaminathan Rajagopal. Any other questions?
So I'm not sure about this, but like for the formula of Ux.
Yes.
So like the formula kind of looks like the formula for tan A plus B.
Very good. Yes, that's a good point. And it suggests that you should go to some new variable called rapidity by writing U itself in terms of a hyperbolic function. Sorry, so that is correct. So the velocity addition formula becomes simpler if you introduce some hyperbolic angles to rewrite this formula. So then it becomes a formula for the sum of hyperbolic tangents, hyperbolic tangent of a sum of angles. So you are absolutely right, and that is called rapidity. So anyway, I've given you the name. One can then look it up and see how the formula simplifies in terms of it.
Yes, sir. Thank you, sir.
Yeah. So if you call V upon C as beta, and then you look at tan H beta, then that quantity has some nice. The formula becomes simpler in terms of that. Yeah, that was Ruptak. Yeah. Anything else? But very good observation. Yeah, this formula becomes simpler in hyperbolic functions. Okay. If there aren't any more questions, I would like to thank you all very, very much for your interest and attention and involvement in the lectures and throughout the course. It has been a pleasure to go through this course with all of you. I hope you have learned some things and enjoyed it. And also, it's not over yet. You still need to submit one thing. But I hope it's a educative experience. All right. So thank you so much for your attention. One thing is I have, though I have learned some names, I still don't know how most of your faces, I don't know. Some voices I am still confusing. So it's a very partial education for me. Anyway, I have learned some of your names, most of them, I think. Okay, so thank you for joining this course, and I wish you all the best. And please keep well and do well in your upcoming exams. And have a nice winter vacation. Thank you so much then. We will end this course and I look forward to receiving your problems at 9. Okay.
Thanks a lot for the course, sir.
Yeah, you're most
Thank you very
welcome.
much, sir.
Yeah, thank you, sir.
Thank you, sir.
Yeah.
Sir, and happy Christmas, New Year.
Yes, sir.
Happy,
Yes, sir.
yes, happy New Year. Happy
Thank you, sir.
Yes,
and
sir. Happy holidays, sir.
yes,
Happy
and
holidays.
Pongal is also coming up. Yeah, so I really enjoyed this course, and I hope you did too as well. All right, so I hope we will see you at CMI at some point also. All right, so I will close this session.
Yeah, thank you so much for the course, sir. Really
Thank you,
enjoyed it.
sir.
Yes.
Thank you, sir.
Thank you so much. Yes, you're most welcome.
Thank you, sir.
Yeah, thank you. And thank you to the TAs, all the TAs, in particular today, Vishnu and Shubham. sorry, no, Shubhendu, sorry, Shubhendu. There are so many, yeah, who have also helped a lot. All right, so we will be in touch. Thank you.
Thank you,
Thanks a
sir.
lot again, sir.
Yeah.